Okay, well, welcome back to our class on algorithms and data structures. We're going to continue on our discussion about bags. In this lecture, we'll get into bag implementations that use arrays. And so we have seen several examples of how to use the ADT bag in a program. In this lecture, we're going to present two different ways, each involving an array to implement a bag in Java. When you use an array to organize data, the implementation is said to be array-based. You will see a completely different approach in the next chapter, as we'll get into. So here's a list of the contents that we'll have that's paralleling what we have in the textbook. And so we begin by using an ordinary Java array to represent the entities in the bag. With this implementation, your bag could become full, just as a grocery bag does. We then offer another implementation that does not suffer from this problem. With this second implementation, when you use all the space in an array, you move the data to a larger array. The effect is to have an array that apparently expands to meet your needs. Thus, we have a bag that is never full. So here we have a fixed side array to implement the ADT bag. And so our task is to define the methods we specified in the previous chapter when we wrote the interface, bag interface. We begin by using an analogy to describe how a fixed size array could contain the entries in a bag. In doing so, we show how the add and remove methods could work. Subsequently, we present a corresponding Java implementation for the bag. So let's talk about an analogy, and the analogy is shown in the figure. So imagine a classroom, we could call it A, that contains 40 desks in fixed positions. And if a course is restricted to 30 students, 10 desks are idle and wasted. If we lift the enrollment restriction, we can accommodate only 10 more students, even if 20 more want to take the course. An array is like this classroom, and each desk is like one array location. Suppose that we number the 40 desks in the room sequentially, beginning with 0, as shown in the figure. Although desks are arranged in rows, in typical classrooms, we will ignore the detail and treat the desks as one-dimensional array. So here we have in the UML notation the details for a fixed-sized array bag. And so now we're getting to the implementation and the core methods. And so before we define any core method, we need to consider the class's data field. Since the bag will hold a group of objects, one field can be an array of these objects. The length of the array defines the bag's capacity. We can let the client specify the capacity, and we can also provide a default capacity. In addition, we will want to track the current number of entries in the bag. So these are the things that we can be talking about. So we can define the following data fields for our class. And so we're showing that, and we'll just leave that there. So we're also getting into the methods and those kind of details in the lower part of this figure. So here we have an outline of the class ArrayBag, and we're getting into constructors. And so let's look at the class ArrayBag as we have described so far. After you complete the header and data fields, you define the constructors. The initializing, which is the second constructor in the listing, performs the steps shown in the previous segment in terms of its parameters, the desired capacity. The default constructor invokes the initializing constructor, giving it the default capacity as an argument. Recall that a constructor can invoke another constructor in the same class, but using the keyword, by using the keyword, this is a method name. After you complete the constructors, you can add the comments and headers for the public methods simply by copying them from bag interface. You can then write empty bodies after each of these headers, and then show the result of these steps. So after this, our next task is to implement the three core methods that are in there. So let's take these one at a time. First, let's talk about the method add. Okay, and so if the bag is full, we cannot add anything to it. In that case, the method add should return false. Otherwise, we simply add a new entry immediately in the last entry in the bag entry by writing. We make sure that we include the statement bag number of entries equals new entry. For your adding to an empty bag, number of entries would be 0 and the assignment would be at position 0. If the bag contains 1 entry, as an additional entry would be assigned to a bag position 1. So after each addition to the bag, we increase the counter number of entries. These steps are illustrated in the fig, and we'll get to that shortly in the next slide in the figure, and is accomplished by the definition of the method that follow the figure. So here is an illustration. If we are adding to the empty bag, number of entries would be 0 and the assignment would be bag 0. If the bag contains 1 entry, as an additional entry would be assigned to bag 1, and so on. After each addition to the bag, we increase the counter number of entries. These steps are illustrated in the figure and accomplished by the definition of the method add. So just some more details. And so here we're just seeing how we can continue along in that process. So once again, this is spelling out the details of the method, and so I won't go through this as much detail, and maybe I should just dwelt on this chart a little bit more with the dialogue that I had. So anyways, now we have the method add. Okay, now we have the method is array full. A bag is full when it contains as many objects as the array bag can accommodate. This situation occurs when the number of entries is equal to the capacity of the array. Thus, is array full has the following straightforward definition as we have shown here in the chart. Then we have the method toArray. The last method is toArray. In our initial core group, retrieves the entries that are in the bag and returns them to the client within a newly allocated array. This length of the new array can equal the number of entries in the bag, that is the number of entries, rather than the length of the array bag. However, we have the same problem in allocating an array that we had in defining the constructor. So we take the same steps as for the constructor. After toArray creates the new array, a simple loop can copy the references in the array bag to this new array before returning it. Thus, the definition of toArray can appear as follows, and we have it here in the text in the chart. There's definitely some implications in terms of security that we want to be thinking about. Practicing fail-safe programming is important. That should include checks for anticipating errors. Validate inputs is important, and redefine incomplete implementations of bag array to make a code more secure. And so a method should not return a reference to its class's private data field. And so this is something that's important. If you have something that's public, that's shareable. If you have something that's private, that's not to be shared. And instead, it should return a reference to a copy of that data field. So let's get into making the implementation secure. Given the present day reality of hackers and unauthorized intrusions into vital software systems, programmers must include fail-safe measures in their code to make programs safe and secure for their users. Although Java manages memory for you, checks about validity of array indices and is type safe, a mistake could make your code vulnerable to attack. You should be mindful of securing as much as you implement ADTs, as adding secure measures to existing code can be difficult. And so this is the method to check initialization. So fairly short. Here is a method add. And so we've already discussed this type of arrangement, except that now we have these assertions and checking the entries. And then we have the code stubs for remove and clear the methods. Remove and clear. Okay, let's talk about having a test program. So the listing here shows a program to test the core methods add into array of the class ArrayBag2. At this stage of its development, initially the main method creates an empty bag by using the default constructor. Since the capacity of this bag is 25, the array should not get full if you add fewer than 25 entries to it. Thus, add should return true after each of these additions. The programmer's descriptive output, in fact, indicates that the tested methods are correct. Note that this version of the class ArrayBag is available on the book's website, and we're also trying to make a lot of that information available through Canvas in our course if you wanted to get it that way. Next, in the main method, we consider a bag whose capacity is 7 and then add 7 strings to it. This time add should return false if an 8th addition is attempted. Again, the program's output that our methods are correct. So this is just more on this listing here, and then we have the output. And so that's just more information that you can review at your leisure. Let's talk more about implementing more methods. Now that we can add objects to a bag, we can implement the remaining methods, beginning with the easiest ones. We will postpone the definitions of remove until we see how to search bag. So the method is empty and get current size. The method is empty and get current size have straightforward implementations. And so you can see that in the text on the chart. The method get frequency of to count the number of times a given object occurs in a bag. We count the number of times the object occurs in the bag array using a for loop to cycle through the array's indices from 0 to number of entries -1. We compare the given object to every object in the array. Each time we find a match, we increment a counter. When the loop ends, we simply return the value of the counter. Note that we must use a method equal instead of the equality operator, which is 2 equal signs to compare the objects. So here we have the method contains to see whether a bag contains a given object. We once again search the array bag. The loop we need here is similar to the one in the method get frequency of, but it should stop as soon as it finds a first occurrence of the desired entry. The following, you could write pseudocode for this, but we're also in this slide, we're actually showing the Java for it. Here is the method that removes the entries. And so we postpone the 3 methods that remove entries from a bag until now, because one of them is somewhat difficult and involves a search, much like the one we perform in the method contain. We will begin with the 2 methods that are easiest to define. First, the method clear. The method clear removes all entries from the bag one at a time. The following definition of a clear calls the method remove until the bag is empty. And so we're seeing that in the slide. What about removing an unspecified entry? And so this is the method remove. The method remove without a parameter removes an unspecified entry from a bag as long as the bag is not empty. Recall from the method specification given in the interface that we saw in the previous chapter. So we can do that one at a time. If the bag is empty before the method executes, the null is returned. Removing an entry from a bag involves removing it from an array. Although we can access any entry in the array bag, the last one is easy to remove. To do so, we access the last entry so it can be returned. Set the entry array's elements to null, decrement number of entries. Decrementing number of entries causes the last entry to be ignored, meaning that it is effectively removed, even if we did not set the location of the array to null. Do not, however, skip this step. A literal translation of the previous step into Java leads to the following definition of the method public T remove, and we have that listing here. What about removing a given entry? Our third method that removes an entry from the bag involves removing a given entry, call it an entry. If an entry occurs more than once in the bag, we will remove only one occurrence. Exactly which occurrence is removed is unspecified. We will simply remove the first occurrence of an entry that we encounter while searching through it. As we discussed before, we will return either true or false according to whether we find the entry in the bag. Assuming that the bag is not empty, we search the bag array much as in the method that we talked about previously. And if an entry equals bag index, we note the value of the index. And so we're getting a chance to see how the remove method works here in the figure. And here is another figure. This is where we can do shifting of entries to avoid a gap when removing an entry. So a gap in the array bag after setting the entry in bag index to null, the array after shifting subsequent entries to avoid a gap, and after replacing the duplicate reference to the last entry with a null. So basically you have a null here and you shift things over, and then you have a null at the end. That's what you're trying to accomplish. Remember that we are not required to maintain any particular order for a bag's entry. So instead of shifting array entries after removing an entry, we can replace the entry being removed with the last entry in the bag as shown in the figure. After locating an entry in bag index, we copy the entry to bag number of entries -1 to bag index. We then replace the entry in the bag number of entries with null, as shown in figure in the bottom there. So we end up getting a similar result in a non-ordered set of group items in the bag. What about the definition of the private method remove entry? So we can go back to some of our previous development in terms of remove. The private method remove entry assumes that the search for the entry is done already, so that we can ignore the first initial step that we had contemplated when we were thinking about this in terms of pseudocode. The rest of the pseudocode, however, gives the basic logic for removing an entry. And so that's some stuff that we can think about. So here is another example of a remove method. And the previous method does not search for the entry to remove, as it removes the last entry in the array. The second method, however, does need to perform a search rather than thinking about the details of locating an entry in the array. Right now, let's delegate this task to another private method, which we could specify. So what's the definition of get index of? The definition of get index of will be the definition of contains, whose so we have that. The structure of the loop is suitable for the method get index of, but we must say the value of index when the entry is found. The method will return the index instead of a Boolean value. So we're trying to figure out how to revise a previous method here. And so the structure to revise a previous loop for use in get index of, we define an integer variable where the record of the value of index where get entry equals bag index. And so we can get the definition of get index. And so that's something that we have here. So here's a revised definition for the method contains. Having completed the definitions of the remove and the private methods they call, we realize that the method contains can call the private method get index of, resulting in a similar definition that was from a previous implementation that we had worked on. Recall that the expression get index of an entry returns an integer between 0 and the number of entries minus 1. So what if we need to resize an array? So the strategy is when a classroom is full, one way to accommodate additional students is to move to a larger room. In a similar manner, when an array becomes full, you can move its contents to a larger array. The process is called resizing an array. So we're showing this. We have the original array that contained 5 constructive memory locations, and another array twice the size of the original array that is another part of the computer's memory. If you copy the data from the original smaller array to the beginning of the new larger array, the result will be an expanding the original array. The only glitch is that the scheme is the name of the new array. You want it to be the same as the name of the old array. You will see how to accomplish this shortly. So the strategy is when a classroom is, so this is just some more details. So suppose we have that array, that my array reference that we saw and that we see in the top of the figure here. We first define an alias old array that also referenced the array as shown in the middle part of the figure. The next step is to create a new array that is larger than the original array and let my array reference this new array as pictured in the bottom. So the new array typically doubles the size of the original array. The final step copies the contents of the original array to the new and then discards the original array, which we see here on this next slide. And so that's one process of how you could do a doubling of an array size. So now we have an alternative steps to resizing array. While we could simply translate the previous, we could be taking an algorithm and converting it to Java. That would be one point. Here we're trying to show a different way where the method's first parameters source array is assigned a reference in the value of my array. Next, the method creates a new larger array and copies the entries in the argument array to it. And the method returns a reference to the new array, and we assign this reference to my array. So just a potential other way that you consider doubling an array or making more room in your bag. So here is a revised definition of the method add. And so we can revise a previous implementation of the ADT bag by resizing the array bag so that the bag capacity is limited only by the amount of memory available on your computer. So we talked about how to go about doing that. And so that's what we're showing here. Okay, so here is the private method double capacity. We resize the array bag using the technique we described before. Because we are increasing the bag's capacity, we must check that the new capacity does not exceed max capacity. And so we make the same check in the constructor, but instead of duplicating that code, we will define another private method that both the constructor and the double capacity can call to enforce the limit of the bag's capacity. And just to finish up here, let's talk about the pros and cons of using Array to implement the ADT bag. And so we talked about two implementations of the ADT bag that use an array to store bag's entries. An array is simple to use, and it enables you to access any element immediately if you know its index. Since we know the index of the last entry in this array, removing it is an easy and fast. Similarly, adding an entry at the end of the array is equally easy and fast. On the other hand, removing a particular entry, if it occurs between two other entries, requires us to avoid a gap within the array. To do so, we replace the removed entry with the last entry in the array. This is an insignificant increase in execution time, as it is overshadowed by the time it takes to locate the desired entry. We'll talk more about such a search later in the book. Using a fixed sized array limits the capacity of the bag, which is usually a disadvantage. Resizing an array dynamically enables you to increase the array size, but requires copying data. You should realize that the array entries that we copy are references, and so do not occupy much space nor take much time to move. Some languages other than Java store the data itself within an array. In such cases, moving large complex objects can be quite time consuming. Okay, well, that'll finish our lecture on this. So thank you very much.